Today, we're going to continue our discussion on basically calculating our Flory free energy for polymer swelling. So we have previously, our total free energy is going to be composed of two components, the entropic component plus our G enthalpic. So we've taken care of the entropic component. We know now what our basically excluded volume V is, and we know what that is in terms of the energy of the monomer units and solvents, and you're now experts in those Flory F Meyer functions. But now we need to kind of take care of this enthalpic interaction, this enthalpic component. So one of the ways that we're going to derive it is a fairly straightforward, or hopefully it's a straightforward kind of derivation and expression. But in order to kind of visualize that, let's go ahead and look at this schematic right here. So one quick note here, this is just going to be r cubed, where r again is just our end-to-end vector for our polymer chain. So concentration is just, and the volume of our polymer is going to be this. Anyways, getting a little bit ahead of ourselves. So our polymer is composed of a number of monomer units. So I'm going to change this to black. Actually, I'm going to change this to blue. Let's just see some difference here. So it's composed of a number, a number of monomer units from 1, 2, 3, 4 to n. So we have n number of monomer units in our polymer chain, as we've done before. Now, we know that in polymer chains, we are going to have intermolecular interactions. So these are the interactions that are available for our monomers to interact with one another. They're going to interact, our E monomer is going to be on the order of basically KT when monomers interact with each other. So those, when a monomer bumps into each other and they interact and they kind of, that polymer fluctuates and it's again dynamic, those polymer chains interactions are going to be on the order of KT when they interact, or when they collide, or they try to occupy the volume of one another, or they run into each other. Those are going to be those intermolecular interactions that occur. So that's going to be the interactions that we're concerned about. So when we kind of want to think about what is kind of the G enthalpic component of our monomer interactions, we could calculate that, or kind of get a sense of how it should scale. So let's keep it simple. So the probability of basically monomer interacting is going to depend on a couple parameters. It's going to depend on the number of monomer units. Obviously, the more number of monomer units, the more probable we're likely to interact. It's going to, so thus we might get a hint about whether it is directly or indirectly related. It's going to depend on the excluded volume as well. So larger excluded volume, larger or more probable that it's going to interact with one another. So my G enthalpic interaction is going to be, and each time a monomer interacts, it's going to have an interaction energy on the order of KT. So it will depend on K, T, N, and V directly. So each time an interaction occurs, it's going to be on the order of KT. And again, as I have more number of monomer units and more excluded volume, again, there should be more probability that those interactions occur. Now, unfortunately, or not unfortunately, but just the nature of this derivation, if my volume of my polymer chain increases, if my, again, approximating like my spaghetti to be in that R to end distance, or the radius of gyration, again, interrelated, we saw by a factor of 1/6 for an ideal chain model. But we could just assume that our polymer, let's say it's a sphere, it's going to be 4/3 pi r cubed. Again, we don't care about prefactors, so volume is approximately on the order of r to the cubed. That's kind of the scaling we're going to see here. So as the polymer chain gets larger and larger and larger, some of these interactions for polymers are going to get less and less likely because our chain is bigger and bigger and bigger. So that is going to inversely affect our enthalpic component. So we're going to have this r cubed factor here. Now, I also want to basically give me my energy density. So I'm going to divide up by the volume again, so that's another r cubed. So this takes into account energy density for the interaction of this single monomer interacting with n number of other monomers. But this monomer can also interact with this monomer and this monomer. So I need to multiply this again by n, and then again to avoid overcounting. In order to not count this interaction twice, I have to divide out by 2. That's it. So in the end, I get an expression that looks like this for my energy density enthalpic contribution right here. And I could use the fact that my concentration of a polymer, C, can be related by this, the number of monomer units divided by R cubed. So, or the number of polymer chains as well. Polymer chains, the number of those monomer units. And so that will be the concentration, basically, of my polymer, C. So that is going to allow me to then write out, I could reuse this expression. So using that relationship here, again, this is R cubed right here. So the concentration of my polymer is just going to be E equals N over R cubed. I could rewrite this expression in terms of concentration, and I could generalize that. So we just looked at basically two-body interactions. So for monomer-monomers interacting, you could do three-body, four-body interactions, and you could get this expression over here. So you could simplify it and just get multiply out by volume, and then you will get an expression like this, only counting the second-order interactions. So that's your enthalpic contribution to your Flory free energy. So next time we are going to look at and derive, combine our terms and look at the Flory free energy. So thanks, and yeah, that's what we're going to be kind of dealing with. Let me know if you have any questions about the enthalpic contribution, and next time we'll get into the Flory full free energy. Thanks. Bye. Addendum. This is not the concentration of polymer. This is concentration of basically my monomers. You know that I make this mistake quite a bit. So just a typo there. I hope you watched the end of this video. Have a good day. See you next time.